This is problem 5-23E. It's on page 254. Steam is leaving a pressure cooker whose operating pressure is 20 psia. It is observed that the amount of liquid in the cooker has decreased by 0.6 gallons in 45 minutes after the steady operating conditions are established, and the cross-sectional area of the exit opening is 0.15 square inches. Determine A, the mass flow rate of the steam and the exit velocity, B, the total and flow energies of the steam per unit mass, and C, the rate at which energy is leaving the cooker by steam. All right, so let me draw the pressure cooker. Let's see, like I said, I'm working from a solution where it's an older version of the text, and so the numbers are slightly different, so I'll try to not make the mistake of just copying from the sheet. So here's our pressure cooker. And there's an opening whose cross-sectional area, A, is 0.15 square inches. There's some liquid inside, and what has happened is the liquid level has gone down from state 1 to state 2. So originally there was liquid all the way up to this line, but now there's not. That change in liquid volume, I've got 0.4 gallons. I think they had 0.6 gallons. And delta T, it took 45 minutes, I think. Yeah, 45 minutes. So there's 45 minutes between states 1 and 2. And of course we've got stuff coming out. Steam coming out, I suppose. There's liquid water in the tank, not in the tank, but in the pressure cooker. We're supposed to find the mass flow rate of the steam and the velocity at the exit. We're supposed to find the total and flow energies per mass. And we're supposed to find the rate at which this mass is carrying energy out of the pressure cooker. Okay. What do they mean by the total and flow energies? What are they talking about there? Well, the total energy, what form of energy would you see in the steam coming out? It's hot, so there must be what? Thermal energy. So that's U. Certainly some U in it, right?
Flow
Some
energy.
thermal energy. There's also flow energy.
What is enthalpy?
And so there's enthalpy leaving. So when they say the total energy, they mean the enthalpy. Yeah, we could include kinetic and potential energy if we really wanted to. But once we calculate the velocity at the exit, we'll compare that magnitude to the enthalpy itself and see if it's significant. Okay? What about the flow energy? How would we come up with the flow energy? Well, that's just this piece. You think we need to take the pressure and multiply it by specific volume? How about if we do this instead? How about if we take the enthalpy and subtract off internal energy? That should give us PV, right? Which is the flow energy. All right, anything else that I've missed? Let's see. Oh, the pressure is 20 psia inside the pressure cooker. And I think that's everything. Okay. So how should we approach this? Any ideas? Well, usually when they give you several things to find, if you find them in order, it will help. So for example, the mass flow rate, that should be pretty easy because we know how much volume has changed. So we should be able to figure out, based on how much volume has changed, how much mass is left. How do we go about that, though? It's going to be proportional to the change in volume, isn't it? Now, of course, this is a rate of mass, and that's an amount of volume, so we're not done. It's not equal yet. How about if we put in per time, however much time has elapsed? Delta T if you want, T, I don't care. I called it delta T here, you can call it T, it doesn't matter. It's just how much time has elapsed. Thank you. So this is now not mass flow rate, but it is a volume flow rate, isn't it? Now, could it be that, the rate of flow actually varies a little bit? Sure, this is going to be an average flow rate. Okay? But it's not yet the average flow rate of mass, it's the average flow rate of volume. So how would I go from volume to mass? Not convert, you can't convert, but you can calculate the mass flow rate based on the volume flow rate. The density, or in other words, the specific volume. So if I just had the specific volume, how would I get the specific volume of the water at 20 psi? Here we have to be careful, because what you might say is, well, it is a vapor leaving, so let's use Vg. You're right, it is, but this is not the change in volume of vapor, this is the change in volume of liquid, so I must use Vf. You see that? Because I'm talking about a change in volume of liquid, not a change in volume of vapor. So if I just had the change in volume, check, the amount of time, check, and the specific volume of saturated liquid at 20 psia, we'd be set. So help me out here. What is the specific volume of saturated liquid at 20 psia? Look that up, please. We're in English units, so it's going to be 0.0 something. 20 psia, saturated liquid, or, well, saturated water. Yes, it is saturated liquid.
.01683.
1683, and those would be cubic feet per pound, right?
Yes.
So if we plug in the numbers, the change in volume is 0.6 gallons. That's pretty inconvenient. We'd like to have cubic feet. Do you see a conversion factor to get us from, or get us into cubic feet from gallons? How many gallons does it take to make up a cubic foot? It's in the conversion table in the back of the book.
231 cubic inches.
It's 7.4805 gallons. I think that's in there. If not, you can write it in. Okay. The amount of time, 45 minutes, but we usually don't like minutes, we prefer seconds, so there are 60 seconds per 1 minute. And VF, you told me, is 0.01683 cubic feet per pound. So what do we have left? Pounds mass per second. So take your calculators, please. Plug all this into your calculator and we'll find the mass flow rate. That's the first step. I guess I need to speed up just a little bit. It's going to be something times 10 to the negative third, like 0.001 something, or maybe even 2.
.00176.
Thank you. Those would be pounds per second. How will we find then the velocity at the exit? Well, that's pretty easy. We can relate velocity to area as follows. The velocity times area equals the volume flow rate, and so, which of course is equal to, but we have to be careful here. This volume flow rate is not that volume flow rate, right? It's not that V dot, because this is at the exit, and at the exit what's happening is steam is leaving. You see that? So I need to multiply the mass flow rate by the specific volume of the steam. So now if I rearrange this to solve for the velocity at the exit, well then all I need to do is take the mass flow rate times the specific volume of vapor divided by area. So I need your help. I need you to look up the specific volume of saturated vapor at 20 psia. I'll start filling in the other parts. There's 0.00176 pounds per second multiplied by VG, which I'm relying on you for, divided by the cross-sectional area, 0.15 square inches. But of course, our specific volume is going to end up being in cubic feet, so let me convert these square inches into square feet. If you will give me the specific volume of saturated vapor at 20 psi, we'll have it.
20.093.
20.093. Thank you. Cubic feet per pound. Gee, just a little bit. There we go. All right, so the pounds are gone, and all but 1 foot is gone, so we'll have feet per second. So the velocity at the exit is however much that calculation comes out to.
33.95.
How much?
33.95.
And everybody agrees with that specific volume? I don't, like I said, I've got different numbers. At 20 psi, the specific volume would be, yeah, it'd take up more space, so I think that's okay. So we've taken care of part A. How about the total enthalpy? How should we do that? Well, the total enthalpy, so this is what, part A essentially, part B. The total enthalpy would just be Hg, right? That's all it is. So all we have to do is look up the enthalpy of saturated vapor at 20 psi. What's that?
1,156.2.
And those would be BTUs per pound. And if we want the flow energy, PV, all we have to do is take the enthalpy of the saturated vapor minus the internal energy of saturated vapor as well, right? So all we have to do is look up one more thing, and that is the internal energy of saturated vapor, UG, at 20 psia. Believe it or not, we're almost done.
Uh, 1081.8.
1081.8 BTU per pound. Thank you. Take the difference between those two. What do we have for the flow energy leaving?
$74.4.
Thank you. So we've got most of the answers that they asked for. We're almost done. Taking care of parts A and B. What about the power output being carried by mass? So part C. Well, power output carried by mass would be the mass flow rate times the enthalpy that it carries. Okay? And so that would be 0.00176 pounds per second multiplied by 1156.2 BTU per pound. If you multiply that up for me, please. It'll be about 1 point something. Because certainly this is a flowing stream, right? So it has flow energy and thermal energy. But wait a second, it has some velocity. What about the kinetic energy? We'll talk about that here in just a second. Anybody have a number for the power output rate?
2.03.
2.03?
Yeah.
Now wait a second. We know the velocity at the exit. Could we calculate the kinetic energy? We could. Let's compare the kinetic energy to the enthalpy and see if it's really all that important. Okay, I'll have to do it over here because I'm out of space. So if we take the specific kinetic energy, that would be v squared over 2, right? So 33.95 feet per second quantity squared divided by 2, and the conversion factor, of course, would be 1 BTU per pound per 25,037 square feet per square second. Again, make sure you've got that conversion factor highlighted in your, the back of your book.
.023.
0.023 BTUs per pound. You think that 0.02 cents is significant by comparison to $1,156? No. So there's no need to even add that in order to calculate the power output. Most of the power output is flow energy and thermal energy, right? As a matter of fact, we can say how much of it exactly is flow energy. Most of it is thermal energy, right? The vast majority of it is. Any questions about this problem? All right, thank you.